Okay, so these are the solutions to the dimension and rank problems. The first one is talking about symmetric matrices that are size 3 by 3. So if you think about this, if I make this like A, B, C, D, E, F, then if this matrix is symmetric, this position also has to be B, this one has to be C, and this one has to be E. Okay, so if you think about that, if you take the transpose of the matrix I just drew, I'm going to get it back. Because the B's are going to swap, the C's are going to swap, the E's are going to swap, the things on the diagonal are going to stay put. So this means that if I'm going to create a basis for this, each of these independent letters has to be treated as though they can change. So I'm going to put a 1 where the A is, and then zeros everywhere else. I'm going to put 1s where the B's are, and zeros everywhere else. I'm going to put 1s where the C's are, and zeros everywhere else. Okay, so now I just have the D. Okay, 1s where the E's are, and a 1 where the F is. And if you look at that set of matrices, you now know that you can build any single 3 by 3 symmetric matrix using these 6 matrices in a linear combination. You just have to multiply the first one by the A, the second one by the B, the third one by the C, the fourth one by the D, the fifth one by the E, the sixth one by the F, and add them all up, and you will get a 3 by 3 symmetric matrix. Now, how many elements are in the basis? 1, 2, 3, 4, 5, 6. So the dimension of the vector space of 3 by 3 symmetric matrices is 6, because it requires 6 elements in order to form a basis. Now, this is not the only basis for this set. This is a pretty easy one to see. There are more than one answer to this, but I wouldn't hazard that there's an easy one to find other than this. All right, so let's look at number 2. Number 2, you can kind of follow the same model that we used for number 1, right? Number 2 gives us this subspace of our 4 called W, and it tells me that I have S plus 4T, T, S, 2S minus T. So every single vector that's in this subspace has that form where S and T are reals. So what I can do is I can create a basis with a vector for the S's, right? So this will be 1 here, 0 S's there, 1 S there, and then 2, 1, 0, 1, 2. And then a vector for the T's, 4, 1, 0, negative 1. And if I do that, I now have a basis for W. Okay, so if you think about this, if you multiply the first vector here by whatever S is, and the second vector here by whatever T is, then we would say that you would get a vector in W, right, for all S and T. So the dimension of subspace W is 2, because there are 2 vectors needed to form the basis. Okay, so let's look at number 3. In 3, 4, and 5, we're working off of this matrix A, which is negative 2, negative 4, 4, 5, 3, 6, negative 6, 4, negative 2, negative 4, 4, 9, right? I need a basis for the row space. So the row space is what I get if I span all of the row vectors in A, right? So the basis would be the minimum set that could be, or a minimal sized set that could be spanned. So I can do this by Gauss-Jordan. That's going to give me, I believe, 1, 2, -2, 0, 0, 0, 0, 1, 0, 0, 0, 0. So ignoring the 0 vector at the bottom there, my basis for the row space will be the vector 1, 2, -2, 0, and then 0, 0, 0, 1. And the dimension for the row space would be 2 then, right? Okay, so this is problem number 3. Now, problem 4 says, what's the column space? You can play the same game, you just transpose the matrix. So the transpose would be 2, 3, -2, -4, 6, -4, 4, -6, 4, 5, 4, 9. If I take Gauss-Jordan of that, I'm going to get 1, 0, and then I think this is 19 over 7, 0, 1, 8 over 7, and then a bunch of zeros. Okay, so again, we ignore the 0 rows, and you could say that the basis here is 1, 0, 19 over 7, and 0, 1, 8 over 7. If you don't like that and you want to pretty it up, you could actually rewrite those vectors by just multiplying them through by 7. So make it 7, 0, 19, 0, 8, 0, 7, 8 would also be another way of writing that basis. This is problem 4. Either one of these is an acceptable answer, because if you think about it, if you just multiply the ones in 3 by 1/7, you get the ones in 2. So these are just multiples of each other. So either one of them would serve as a basis of the column space of A. Since the basis of the row space has 2 elements, the basis of the column space has 2 elements, the answer to problem number 5 is the rank. And the rank of A is the size of either its row space or its column space, which is 2. The dimension of the row space or the column space, which is 2. So there you go. That's 3, 4, and 5. All right, so let's look at number 6. 6 gives us a set with 4 vectors, and then asks us for a basis for the span. So the span of S is going to be all the linear combinations of the vectors in S. But if the vectors of S are not linearly independent, they're not a basis, because the bases have to be both linearly independent and spanning. So span S is, I mean, we're definitely getting something that spans, but we're not getting something that's necessarily linearly independent. So let's take a look at this. Just throw the vectors of S into the rows of a matrix. 2, 9, -2, 53, -3, 2, 3, -2, 8, -3, -8, 17, 0, -3, 0, 15. And then if I take Gauss-Jordan of this, I end up with 1, 0, -1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, which means that these 3 vectors will form a basis for the span of S. So the first one is 1, 0, -1, 0. The second one is 0, 1, 0, 0, and the third one is 0, 0, 0, 0, which means that the span of S has a dimension of 3. Okay, so let's look at number 7. Okay, so number 7 is the span, or the set of all vectors that can, when taken a linear combination, the set of all coefficients that will give you a linear combination that will give you a 0 when you use this to solve a system of equations. So if I took a times x is equal to the 0 vector, right? And let's say big X is the set of all little x such that, little x, not x bar, little x such that ax is equal to 0, then X is the null space of A. So literally what I can do here is set up the system of equations. Put A as the left side of the augmented matrix. And the 0 vector as the right side, because Gauss-Jordan says this is solving this system of equations. We do our REF here, and something interesting happens. I get just the trivial solution, right? I get that all of the coefficients could be 0. So in the end of the day here, A is invertible, which means that these vectors are actually linearly independent, which means that the only solution that you have to this system is the 0 vector, which ultimately means that the basis is just the 0 vector. And when we have a basis that is just the 0 vector, we say that the dimension of the null space here is 0. So there you go. That's it. That's all for the dimension and rank problems, and we'll pick up from there. I hope you're all healthy and happy, and hope to see you and hear from you soon. If you have questions, drop them in an email or do one of the drop-in sessions, and we'll go from there. Thank you.